Good afternoon, everyone. In previous lecture, we have studied about the elimination reactions and the different types of mechanism that are E1, E2, and E1 CB. And what is the difference between these mechanisms? As well, we have also learned in the previous lecture why elimination reactions are preferred over the nucleophilic substitution reactions. But in today's lecture, I will discuss some factors, how these factors decides the fate of reaction. Either it will proceed via E1 mechanism or E2 mechanism. As well, I would like to describe some factors why elimination reactions are preferred over substitution reactions. These all factors we have discussed in the previous lectures. For this, the bases should be bulky in nature and the nucleophile should be a strong base. If the reaction is carried out using high temperature, it will prefer to undergo elimination reactions. So then moving towards factors affecting the elimination reactions. The first one is nature of base. If we have been using strong base such as alcoholic KOH or ethoxide anion, then the reaction will proceed via E2 mechanism. If we have been using weak base such as water, ethanol, these are the weak bases, then the reaction will proceed via E1 mechanism. Because in E2 mechanism, the both the H positive and the leaving group are abstracted simultaneously at the one time. If the base is strong in nature, it will abstract the hydrogen as well as with the removal of leaving group. But in case of if we are using weak base, the first step is the removal of leaving group. Then secondly, it will abstract the proton because the removal of leaving group will facilitates the abstraction of proton. Thus, this is the concept behind the nature of base, how it affects the fate of reaction either E1 or E2. The second factor is the nature of substrate. Let's study about the nature of substrate. Look at the first example. In this, I have taken tertiary alkyl halide. Tertiary alkyl halide. So if it is proceeding via E1 mechanism, in E1 first is removal of leaving group. So we have removed the leaving group from here and there is formation of a carbocation. This carbon carries a positive charge. In the second step, the base will abstract the hydrogen and this bond will be broken and there will be formation of a new bond which leads to the formation of alkene. Clear? So this reaction is proceeding via E1 mechanism. So it here we can summarize that substrates in which there is formation of stable carbocation, only those reactions will proceed via E1 mechanism. Yeah. See, look at the next example. In this, we have been using allylic halide. 1, 2, 3, 4. So this is allylic halide. So if the leaving group is removed from here, then it will form a carbocation. Just wait a second. It will form a carbocation. So this carbocation can be stabilized. How this pi bond will give electron to this carbon and Now, this is a carbon number 1, 2, 3, 4. Now, there is the positive charge on the carbon number 1 and the double bond between carbon number 2 and 3. So by this way, the here the carbocation is stabilized. Thus, it is yielding a product that is alkene. So this is elimination product. Look at the next substrate here. This is benzyl chloride. If the leaving group is removed from here, then here also there is formation of a carbocation. This carbocation is stabilized by the pi electrons of benzene ring. There will be formation of so many resonating structures, and thus this carbocation will be stabilized. So I would like to draw the resonating structures of benzylic group here so that you can understand the concept more clearly, how this can stabilize the carbocation. First of all, this pi bond will shift here. I would also like to mark these carbons 1, 2, 3, 4, 5, 6. So the pi bond between carbon number 1 and carbon number 2 is shifted towards this carbocation, thus forming the double bond between these two carbons. Here there is no CH2. CH is there only. Now the positive charge is acquired at carbon number 2. Again, there is shifting of pi bond from carbon number 3 to carbon number 2. And the positive charge is moving throughout the whole benzene ring via resonating structures, CH3 double bond. So you just mark the carbon 1, 2, 3, 4, 5, 6. Now look at the carbon number 4. Now the positive charge is at carbon number 4. Again, the carbon number 5 will transfer its pi electrons to carbon number 4. Then there is double bond between carbon number 4 and 5, and the carbon number 6 will acquire positive charge, CH, CH3, CH. Then again there is movement of pi electron and thus forming the initial structures. Okay. So by resonating structures, this carbocation can be stabilized, thus forming final product alkene. Another type of substrate is alpha heterosubstituted. In these alkyl halides, this is substituted with alpha heteroatom. Here they have taken oxygen as heteroatom. So oxygen has lone pairs. It can give its lone pair to this carbon, and which facilitates the removal of halogen group. So the lone pairs of this oxygen are helping in the removal of halogen group. Thus, oxygen is acquiring positive charge and there is formation of a double bond between oxygen and carbon. So it is helping in the stabilizing of carbocation. Then again, in next step, base is abstracting hydrogen from here. Then there is the formation of bond, and the bond between carbon and oxygen is breaking. It is converting into a single bond. This finally led to the formation of alkene. So these all are the examples in which it follows even mechanism. Next is secondary alkyl halide. Okay, secondary alkyl halide, there is only one alkyl group after the elimination of this halide group, as this is secondary carbocation because it is linked to two alkyl groups 1 and 2, so thus it is called as secondary carbocation. It is less stable than tertiary carbocation. That's why uh, it may also be eliminated by E1 mechanism, but it can also undergo E2 mechanism. The all examples we have done, such as tertiary alkyl halides, secondary allylic benzylic. These can also undergo E2 mechanism, but these are more favorable to undergo via E1 mechanism. Okay, so there are more examples which never be eliminated either by E1 mechanism. If the halide group is removed from here, then this carbon acquire positive charge. This is primary carbocation. It never undergo E1 mechanism. It here the elimination will be proceed via E2 mechanism. So you can summarize the natural substrate over here. The tertiary carbocation prefer to undergo via E1. Secondary like to undergo via E1 as well via E2. Primary would like to undergo elimination only by E2 mechanism. Okay, there are some another substrate which cannot undergo elimination reaction either by E2 or E1 because in this substrate, there are no alpha hydrogens. There are no alpha hydrogen. You can see here. This is methyl group and it is linked to halogen group. There is no further group, so it do not have any kind of alpha hydrogen. So it cannot undergo any kind of elimination reaction by either mechanism, E2 or E1. Similarly, it is true in case of benzyl bromide. Okay, this is alpha carbon. Look at this alpha carbon. This alpha carbon is attached to this CH2 group, 1 sigma bond, 2 sigma bond, 3 sigma bond, 1 pi bond. So this carbon is forming 4 bond, 3 sigma and 1 pi bond. This carbon have no alpha hydrogen. So as there is no alpha hydrogen, it do not undergo any kind of elimination. This is tertiary butyl bromide. So hmm, okay, no, we cannot use this example over here. No, there are some examples of elimination reactions. We will do these reactions one by one and study how these reactions are proceeding. The first one is cyclohexanol. So just check the nature of substrate. This is secondary alcohol as it is linked to carbon and this carbon. So this is secondary alcohol. And also check the conditions, high temperature prefer elimination reaction. So this will undergo elimination reaction instead of substitution reaction. So this is the first factor we have been deciding whether it is elimination or substitution reaction. Another one is we have been using here solvent, water and H3PO4. So providing acidic environment means we have been using protic polar solvent. Protic polar solvent, thus as well here is secondary alcohol. It will proceed via E1 mechanism and gives the product that is alkene. Another example, here this carbon is attached to phenyl ring and two more carbons. So this is tertiary alcohol. Tertiary alcohol, again we have been using acidic conditions, protic polar solvent. This reaction will also proceed via E1 mechanism. In this, first of all, what is the role of acid here? This acid will protonate this OH group. After the protonation of this OH group, oxygen will acquire positive charge and OH2 positive act as good living group as compared to OH group. That's why this reaction is conducted in the presence of acidic group. As this OH2 positive is acting as good living group is removed at first step, thus forming a carbocation. In second step, the water will abstract hydrogen from here and this there is formation of a double bond. Clear? So this reaction is proceeding via E1 mechanism. So these are the certain examples which showing how the nature of substrate affects the mechanism of the reaction. Look at the this structure. This is bicyclic structure. Okay, in bicyclic structures as well, here is the presence of a bridge. This OH group is attached to the carbon which is forming bridge over here. When this OH group is protonated, it forms O positive H2. Okay. If we remove the H2O from here, clear? Then there will be formation of a carbocation, which is not possible because this carbon is non-planar, because this carbon is a part of the bridge. Here this carbon is forming bridge. This carbon is non-planar. As we know, carbocation are planar in nature. Only the carbocation which are planar in nature are stabilized because they have configuration they have hybridization sp3. But this is non-planar. This is not stable in nature because this entity has high energy. Course, those species having high energy are very unstable. So this is also true according to Braddock's rule. The bridged bicyclic carbocation can't be formed because of high energy. Clear? So these are the some few examples of substrate which can undergo E1 and E2 mechanism. I have explained very clearly one by one. The next is the nature of living group. How the nature of living group is affecting the mechanism E1 and E2. If the substrate is CH3, CH2, Cl, I am choosing just simple substrate in which the living group is halide. Then it will it will prefer to undergo E2 elimination. E2 means only in one step. Proton and the both leaving group are removed simultaneously in case of E2 because halides are good leaving group. Okay, so alcohols. If we have been talking about alcohols, this OH group is bad leaving group. Bad leaving group. So it would like to undergo E1 mechanism. How it will proceed via E1 mechanism? First of all, this OH will be protonated. On protonation, what happen? It act as good leaving group. Then this OH2 group will be removed, thus forming a carbocation. Then this is alpha carbon. Then hydrogen will be abstracted from alpha carbon, forming alkene. So this was just, I am giving the overview how this will get mm, uh, this will proceed via even mechanism. So as we have discussed about the halide, where the living group is halide, alcohol, moreover tertiary quaternary amines, such as, first of all, what is amine? Amine group is NH2. This is amine group. But we have been talking about tertiary amines. Tertiary means it is linked to three methyl groups. Okay, this is tertiary amine. And what is quaternary amine? If this nitrogen will attack on this methyl group, it will get this methyl group with the removal or with the loss of lone pair. So there will be positive charge on nitrogen. This is our quaternary amine. Okay. In quaternary amine, it is attached to four methyl groups. In tertiary amine, it is attached to only three methyl groups. As nitrogen has valency of three bonds, it can form three bonds. Okay, but it can extend its valency up to four by losing its lone pair. Let's look at the example. So these are the methyl groups here, carbon and NME2. First of all, it will undergo nucleophilic substitution reaction in the presence of methyl iodide. There is a partial positive charge on methyl group and the partial negative charge on iodine group. The lone pair of nitrogen will attack on this methyl group and with the removal of iodine. So this nitrogen is methylated. As there is addition of a one methyl group to nitrogen, we will use the term methylated as well. It acquires positive charge because it has given its electron to the methyl group. Now, here this is a sign of high temperature. We have been using KOH. Clear? Hmm. So, here what is our concern, whether this reaction will proceed via E1 or E2. Okay, so previously we have discussed the nature of substrate. If this is if it proceeds via E1, means two step. In this there will be formation of a carbocation. If the carbocation is stabilized, then it will prefer to undergo E1. If the carbocation is not stabilized, it will like to proceed via E2 mechanism. So I have drawn this carbocation if it is proceeding through even mechanism. We are just supposing if it is proceeding through even mechanism. Here there is formation of a carbocation. You can see this carbocation is attached to further one carbon. So this is primary carbocation. Primary carbocation would like to prefer to undergo E2 mechanism. In this, there will be abstraction of base and removal of living groups simultaneously, and thus forming a double bond alkene. So this is our final product. So it will proceed via E2 mechanism because in this case the carbocation is less stable. Consider the another case in which the leaving group is N positive Me3, means quaternary amine. The leaving group is quaternary amine, but the substrate is different. Here leaving group is attached to tertiary carbon. Okay, so again we have been supposing it is proceeding via E1 mechanism. What will happen in E1 mechanism? First leaving group is removed, thus forming a carbocation. So this is tertiary carbocation. Then H, H, H. This water will abstract the hydrogen from air and form a double bond. Yeah. So basically, it depends upon the nature of the substrate to which it is attached. Clear? In the first case, we have also been using a strong base. In second case, the water is a weak base. These all factors decides whether it is E1 or E2. So we have to focus on the first substrate. If it is stabilized, then it will proceed via E1. If the carbocation is not stabilized, then it will proceed via E2 mechanism. As I discussed, alcohols. Alcohols undergo E1 mechanism. Yeah. Alcohols can also undergo E2 only under certain conditions. If the alcohol group is protected with some other group, such as if the reaction is carried out with methyl tosylate, this is methyl tolulyl chloride, sulfoxide tolulyl group, okay, para, you can say para tolulyl sulfonyl chloride. This is para tolulyl sulfonyl chloride group, and both were supposed to react under nucleophilic substitution reaction. Here OH will attack on this sulfur and the Cl will be removed from here. Thus, this forming a bond between this OH group and sulfur group. Here, OH is protected. Protected means it is converted to some other group. Clear? This oxygen has no free H group. So this group acts as a good living group as compared to OH group. Thus, we have converted it into some another species. So here is the example. In this, OTS is a living group. This is formed by converting by first of all carrying the reaction with the this paratolized sulfonyl chloride. Thus this group is formed, and we have been using here a strong base which is bulky also, tertiary potassium tertiary butoxide, O negative, CH3 CH3 CH3. So this reaction will proceed via E2 mechanism. It is only true if this OH group is protected with some another species. Clear? Hmm. So next is the nature of solvent. So this is our fourth factor. Nature of solvent. If we have been using polar protic solvents such as H2SO4, H3PO4, then the reaction will proceed via E1 mechanism. Otherwise, such as DMF, DMSO. These all are polar aprotic solvent. Then reaction will occur via E2 mechanism. Same is true in case of nucleophilic substitution, as we have already discussed in case of nucleophilic substitution. In case of nucleophilic substitution, if we were using polar protic solvent, then it will undergo via SN1. If polar aprotic, then SN2. So both have the same case. Why polar solvent? Why polyprotic solvent favors E1? Because polyprotic solvent stabilizes carbocation. As in E1 mechanism, first of all, there is formation of a carbocation. So if the solvent is polar protic, clear? It's H2SO4. Just wait a second. Single bond OH OH. As this solvent is protonated, the negative charge on here will stabilize the carbocation. So this was all about the nature of the solvent, which kind of solvent is favoring E1 and E2 reactions. So I have summarized all the factors here, how these affect the mechanisms. If we have been using methyl halide here and in the presence of poor nucleophile H2O or ROH, then it do not go undergo any kind of reaction, either substitution reaction or elimination reaction. Substitution reaction, because the nucleophile is poor, it cannot replace this halide group, and it also cannot undergo elimination because there is no alpha hydrogen. So this is the case here. Okay, if I have been using weakly basic, weakly basic means now it is better nucleophile as compared to water and ethanol, so it can undergo nucleophilic substitution reaction but via SN2 mechanism, means which includes only one step, the attack as the removal of leaving group. Both are in simultaneous step because there is no steric hindrance in this molecule, so it can undergo SN2 mechanism. If I have been using strong base, also it will proceed via again SN2 mechanism. If strong base is not sterically hindered, such as CH3O negative, this is not sterically hindered. If I have been using sterically hindered base CH3, CH3, CH3O negative, tertiary butoxide, then again it will undergo only SN2 mechanism because there is no possibility of elimination reaction in this due to the absence of alpha hydrogen. But in case of poor nucleophile, it will not undergo any kind of reaction because nucleophile have no ability to attack on this carbon which is linked to halide. Okay. The second case I have using is primary alkyl halide, which is unhindered. There is no steric hindrance. Clear? When there is no steric hindrance, it can undergo SN2 mechanism. Clear? Same if the nucleophile is poor, it will not attack, it will not undergo any kind of reaction. If the strong base is used when it is not hindered, means unhindered, CH3O negative, such as, again it will undergo nucleophilic substitution reaction via SN2 mechanism. If the hindered base is used, such as tertiary butoxide, and we have taken primary alkyl halide, then it would like to prefer E2 mechanism because here elimination is preferred over substitution because the base is bulky in nature. So this was the condition for the elimination reaction. Okay, then the next is primary alkyl halide, but here the substrate is sterically hindered. Okay, now here substrate is also sterically hindered, but in case of poor nucleophile, again no reaction. If weak base, it will undergo SN2 substitution reaction in one step, means nucleophile will attack, sorry, I negative will attack from here and the leaving group is also lost in one step. Okay, now here we have been using strong base, whether it is hindered or unhindered. In both cases, it will undergo elimination reaction because here the base used is strong. As well, here there are two conditions. Substrate is also sterically hindered. Okay, base is also strong, either hindered or unhindered. Clear? So both these factors favors elimination reaction. But here base we have been using was weak, but the reactant was sterically hindered. So it was preferring SN2 because the base here is not strong. So there was the condition also for elimination reaction, base should be strong. Then the next two, secondary alkyl halides. Secondary alkyl halide. So if we have been using poor nucleophile, it can also undergo SN1 and E1 mechanism. both, because this is sterically hindered. E1 means two steps mechanism. SN1 means this is also two-step mechanism. So first step in both is there is formation of a carbocation. If there is formation of a cation in SN1, nucleophile attack, okay, and but in E1 the proton will be abstracted. Clear? But this is slow because the substrate is secondary halide. Clear? Okay. If the base if the nucleophile is weakly basic, not too strong, it would like to only prefer SN2 mechanism, only substitution, because the nucleophile is weak. Yeah. So it is proceeding here via even, as we have already discussed. If the we have been using weak base, it can also undergo even reaction, because in even there is first of all removal of the leaving group. Then this nucleophile or base will attack on the hydrogen. But here there is a no base. Clear? Here base is acting as a nucleophile. It is not abstracting any kind of hydrogen. So it will proceed via SN2 mechanism. Okay. Again, strong base, either hindered or unhindered, and substrate is sterically hindered. So it would like to prefer undergo E2 mechanism in both cases. Either base is hindered or unhindered. Okay. Then discussing the case of tertiary alkyl halide. Tertiary alkyl halide, saying this is sterically hindered. Sterically hindered. So it would prefer to undergo E1 mechanism and SN1 mechanism. But these are fast as comparison to secondary halide. Okay. Okay, then if weak nucleophile is here, then it can also undergo SN1 and E1, matlab both elimination reactions, because the substrate is bulky. Here the substrate is bulky. So it is preferring to undergo elimination reaction. E2 elimination here is not possible. E2 means in one step. In one step, the base cannot abstract the hydrogen along with the removal of halogen, because this is sterically hindered reactant. Clear? If the if the base is strong in case of tertiary alkyl halide, then it can undergo simultaneously elimination reaction along with the removal of halogen, means abstraction of hydrogen H positive as well as removal of halogen, both in one step. So when the base was weak, it was undergoing only E1. So this is all the summary of regarding nature of substrate, as well as it is also covering the nature of base. Clear? So here it is covering two factors and comparing SN1, SN2, E1 and E2 mechanism. Clear? So we have already discussed the nature of the solvent. In the nature of solvent, protic will favor E1, protic polar or protic will favor E2 mechanism, as well as the nature of leaving group. If there was the OH, then it would like to prefer undergo E1 mechanism. Otherwise, it will be eliminated via E2 mechanism. If the OH group is protected, then it can also undergo E2 mechanism. Yeah. So today's lecture all about was the factors affecting SN1, SN2, E1 and E2 mechanism. Clear? So our next topic will be the stereochemistry of products formed in E1 and E2 mechanism, because in both E1 and E2 the final product is alkene. The alkene may be cis and trans. Clear? Or it may be regio selective, the alkene may be formed in the particular region along between carbon 1 and 2, 1, 2, as well between carbon number 2 and 3. So here the reason is different. Here is the case of diesel-selectivity. In this case, both have different stereochemistry. This is trans and this is cis. So which in which reaction in E1 what kind of product is formed, either cis or trans, as well in E2. We will study this in the next lecture. Then it will cover our whole and elimination reactions. Thank you. So share and subscribe my channel. If you have find any kind of query, then you can ask me via comment.